Wow, hello guys, welcome to my channel. You're especially welcome to Master Builders Online Academy, the only online academy where you can learn all the tips as to how to handle engineering problems, especially complex engineering problems, right? So, but before then, I want to sincerely appreciate every one of you who are subscribers of this channel. Thank you for subscribing to our channel, and then thank you for liking our videos, sharing our videos, and then leaving positive comments at the comment section of our videos. We so much appreciate everything that you're doing here. Even though we do not know you in person, we appreciate you. We are where we are because you always come over here to check out our updates. So guys, in this lesson, I'll be showing you again how to solve basic and complex engineering thermodynamic problems without wasting much of your time. So in this particular module, I'll be solving two basic problems, and these two questions will actually blow off your mind if you truly stay tuned from beginning to the end. Do not skip any part of this video because everything that we'll be doing here are principle based. All right, and as you can see on the screen, we have the very first question before us. Okay, and now we have that 5 kg of nitrogen is heated in a reversible, not irreversible, in a reversible. That means this process is reversible. No flow constant volume process. Constant volume process. Constant volume process. Are you there? Okay. Now, one of the things is that for constant volume process, as we initially know, anytime you are dealing with constant volume process, it shows that work done is equal to 0. There is no work done. But let's progress first. Now, till pressure becomes 3 times the initial. Full stop. The initial temperature was 100 degrees Celsius. Full stop. Now, the first question now says that we should determine the final temperature. Then the second question, the change in internal energy. Third question, the change in enthalpy. Then the last question, heat transferred. And guys, this is very, very simple for us to do, but it's quite different from the problems we've solved before now, all right? Because in that question, we'll be given heat, we'll be given work done, and then we are now asked to calculate for either internal energy or whatever. But this case is quite different. So, but all we just need to do now is to list out the given parameters. All right, so given, what are we given? We're told we have mass of the nitrogen gas. So let's take it as M, which is 5 kilogram. This is the mass. And then we were given volume. Okay, and then we were told that V1 is equal to V2, and then both is equal to V. We may not even need this one as long as the volume is constant. That means there will not be any point where we'll be using this volume. All right, then as we read further, we also have pressure given, right? Pressure. And now this pressure will have initial and it also have final. But as we read through the question, we're told that till the pressure becomes 3 times the initial. But we do not know the initial, so we simply just call it P. That's how we have it. So then the condition now says that the final pressure, which till as the process continues, we now have this. So the initial pressure is P as we take it now, and then the final edge pressure becomes 3 times P1, whatever value that P1 has. And then we can have this as T times P because pressure 1 is P. So whatever value pressure 1 is, because in exam you can be given pressure 1 as, take for instance now, 50 Newton per meter square or 50 megapascal. So if you are given the same thing, whatever you have as pressure 1, multiply by 3. Are you there? Whatever you are given as pressure 1, all you just need to do is to multiply it by 3 to get pressure 2. Are you there? Which is the final pressure. But like this case now, since it is not given, the initial pressure is not given, so we just assume it to be P. And then the final pressure is 3 times P. Are we there? Then again, as we look at this problem, the last statement mentioned that the initial temperature was 100, as you can see here. Can you see it here? All right, so we have temperature. Are we there? So temperature, we have initial and then we also have final. So the initial temperature is giving us 100 degrees Celsius. But remember that we do not solve in Celsius. We solve in Kelvin. So how do we now convert this 100 degrees Celsius to its equivalent value in Kelvin? All we just need to do is to add this 100 to 273. So 273 plus the value in Celsius will now give us the equivalent result in Kelvin, which will give us 373 Kelvin. Hope you understand this. So peradventure this question came in Kelvin, you don't need to convert. But once you have it in Celsius, degree Celsius, you must always convert to Kelvin. Understand that Kelvin does not have a degree as a symbol, right? You only have Kelvin, not 373 degree Kelvin. It's wrong to have it that way. Only Celsius is in degrees. All right. Okay, so if this is clear, now we have final temperature unknown. So now let's come back to the question. We have been able to extract this, and then from the question again, we were given, let's list those parameters here. We are given that R is equal to 0.297 kilojoule per kilogram per Kelvin. And again, we are given CV as 0.744 kilojoule per kilogram per Kelvin. I hope you understand what is happening here. But we are not given constant pressure. So if there is an equation that requires us to use constant pressure, we will obtain it. Remember that CV is specific gravity or specific weight at constant volume, and then the other is at constant pressure. Okay. So now the first question that we have here now is for us to find the final temperature. Final temperature. Final temperature. So how do we find the final temperature? Number one, final temperature. All you need to do now to be able to find the final temperature is to relate the given parameters with that of temperature. Now remember, when volume is constant, what you have is actually what we call Charles law, right? It's in Charles law that volume is constant, or you can actually use the general ideal gas equation, anyone you want to use. Let's use that. Remember that PV over T is equal to constant, right? You remember this equation, which by extension P1 V1 over T1 is equal to P2 V2 over T2. Now, because volume is constant, at constant volume, the equation reduced to P1 over T1 is equal to P2 over T2. I hope you can see this. All we just need to do now, since we are looking for T2, we just need to make T2 the sort of formula from here. All right, we have that T2 is equal to P1 is equal to P2 times T1 all over P1. Just make it sort of formula. And then what is P2? P2 is 3P multiplied by T1 is 373. And then P1 is P. Just come up here and see the values we have. We said that P1, let it be P, and then P2 became 3P. And then T1 is 373. Then we are looking for T2. Hope you understand what is happening here now. So now, at this level, after substituting for P2, T1, and then P1, we find out that P will cancel out P. P will cancel out P. So if P cancels out P, we now have 3 multiplied by 373 Kelvin. Don't forget that the value will be in Kelvin. So these two are giving us. So by the time we multiply 373 by 3, our answer becomes 1119 Kelvin. This is the answer we have. But take for instance that this is an objective question, and then when you check out your objective, you find out that the result is not in Kelvin. How do I now convert from Kelvin to Celsius? It's very simple. To convert from Kelvin to Celsius, all you just need to do is to remove 273 from 119. It's as simple as that. 273 from 119. 273 from 119. It's as simple as that. Or recall that now value in Kelvin, look at it, is equal to temperature in Celsius, degree Celsius, plus 273. So since I want to find in this, I'm going to have in Kelvin minus 273. So we'll have 1119 minus 273. And if we do this, so this is how we are able to find the final temperature by removing 273 from 119 to have 846, and then we have this. The final temperature becomes this. So the next thing we want to do now is to find the number 2, the change in internal energy. And now in this case, to find change in internal energy, because of the presence of pressure, temperature, and volume that we have here, we have an equation to be able to find this. Are we there? There is another equation to be able to find this. So let's put this down. B, or okay, question number 2, let's call it 2. The change in internal energy, which is this guy. This is the symbol, right? So when these thermodynamic properties are given volume, temperature, and pressure, this change in internal energy is given as mass multiplied by CV into change in temperature multiplied by change in temperature. By extension, this is M CV into T2 minus T1. Are you there? So change in internal energy becomes our mass. If you look at the question, we were given mass. Our mass is 5 kg. Then just for us to substitute, CV is 0.744 as we have it there, right? Okay, so we come here, I'll put in the value. So mass is 5 kg multiplied by CV is 0.744, and then multiply by temperature 2 is 119, we just calculated for, and temperature 1 is 373. Then we close the bracket. Then change in internal energy becomes 5 multiplied by 0.744 multiplied by, if we remove 373 from 119, we will automatically have this result as 746. And our final result, if we multiply this out, becomes 2775.12 kilojoule. This is the answer to this very question. It's as simple as A, B, C. Simple as this. Now the next question we are asked to also look at, as you can see here, question number 3, is that we should find the change in enthalpy. Change in enthalpy. Change in enthalpy. And how do we find this change in enthalpy? To find change in enthalpy, we also have a formula for that. Okay, so 3. Change in enthalpy. And this is given as delta H. So change in enthalpy is given as MCP into change in temperature. And then this is equivalent to MCP T2 minus T1. All right, so by the time we put in the values, we are good to go. Now that we have stated this equation, we now say but. Remember, from the question, CP was not given, but we can find CP from this relationship. Okay, R plus CV. This is how we can find CP. And then when we're given R, we're given CP. So if we scroll up, we have already used R before. See the values as we have them. R is 0.297, and then C is 0.774. Okay, so let's come down here so that we can find CP. I hope you are following up. So we have 0.297 297 plus 0.744. By the time we add them up together, R becomes 1.041 kilojoule per kilogram per kV. So this is the CP. Now that we have gotten CP, which is specific weight at constant pressure, we just have to substitute into our formula. All right. So in order to substitute into the formula, all we just need to do is to come up with delta H is equal to, remember, M is 5 multiplied by, now CP is 1.041, then multiply by change in temperature, T2 is 1119 minus 373. We have obtained this before, so this will give us 5 multiplied by 1.041 multiplied by 746. Now by the time we multiply out these results, our outcome becomes 3883 kilojoule. So this is the internal, this is the change in enthalpy. This is the change in enthalpy. I hope you understand this. This is the change in enthalpy. Now finally, if we move up to question number 4, we are actually asked to find the heat transfer at constant volume process. Remember, work done is 0, right? So in this case now, let's put down Roman figure 4. All right. So 4, we have heat transfer, okay, which is Q. So to find heat transfer, understand that at constant, let me just state it here, at constant volume process, comma, work done W is always equal to 0. No work is done, so it means work done is equal to 0. And then from Roman figure 2, we have already calculated for change in internal energy. We calculated for this, and then we have this as, what do we have this to be earlier? This becomes a value that we have somewhere around there. If you check up here, that's the value we have here, which is 277 whatever. So let's assume we say this is not known, for instance, but let's just put a value there. Okay, this is 277.5.12 kilojoule. All right, then we are looking for heat transfer. So we have Q is equal to unknown. So again, as you can see from these three model or these three parameters, you find out that we can actually use the first law of thermodynamics equation to actually get the value of heat. So we just simply recall that heat minus work done is equals to change in internal energy. And now because we are looking for heat, we can just make heat instead of formula, and then we have W plus change in internal energy. And now we understand that W is 0 for this process, right? So we have 0 plus change in internal energy. Therefore, Q is equal to change in internal energy. So what does this have to tell us now? It is very, very clear to us that anytime work is 0, the heat transfer is the same thing as the change in internal energy. I hope you understand it. So the value we have for that is 2775.12 kilojoule. So we have successfully obtained the heat flow for this particular system. So you find out that it is very, 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 very simple to solve any thermodynamic process, any thermodynamic calculation problems effectively. All you just need to do is to understand the conditions and then understand the basic formula that will actually help you in any aspect of engineering thermodynamic calculations that you are looking into. So I hope you have actually learned a lot from this particular video. So don't forget to like this video, don't forget to share this video, and don't forget to leave a comment at the comment section. If you are new here and then you are not yet subscribed to this channel, do consider subscribing to our channel and ensure you turn on post notification bell for more exciting content, so that whenever we upload mind-blowing content, even while you are asleep, wherever you are, you will be notified. Thank you for watching. Let me show you again another problem where we also apply some of these equations to your own benefit. Without further ado, let's dive into that question. All right, guys, welcome again. Welcome to our channel. Now we have another question with us. Remember that this is a continuation lesson. On the screen, as you can see, we have 85 kilojoule of heat as supplied to a system. That means accepted by the system at a constant volume. Constant volume. Don't always forget constant volume. At constant volume, what happened? Work done is equal to 0. Remember the problem we just solved before this particular one, right? Now let's continue. Then the system rejects 990 kilojoule of heat. Okay, this of heat at a constant pressure of this, and this of work is done on it. Now don't forget that at constant pressure, like we have now, there exists work done, there exists heat. Are you there? At constant, then and the work, and then we now have a work done on that process is this. As you can see, the system is brought to its original state by adiabatic process. All right, now the question is determine the adiabatic work, which is number 1. Determine the adiabatic work. Let me change the color. This is it. Determine the adiabatic work, and then again determine the value of internal energy at different values like we have here now. Let's change this to this color. So this is it. So we're asked to determine the adiabatic work and then also determine the values of internal energy at all end states if initial value is this. Now, looking at this diagram, what this diagram will help us to do as far as this is concerned is that if we start from point 1, if the journey begins from point 1, just as you can see here, and then move to 2, and then from 2 to 3, and then from 3 back to 1 through adiabatic process like we have it now. And then the internal energy at point 1 is what is given as 100 here. Then the internal energy at point 2, that's what we are asked to look for. The internal energy at point 3, that's also what we are asked to look for. Don't forget, we are also asked to calculate for the internal energies. Haven't been given the internal energy at point 1, which is the starting point. I hope you understand this. So because we have series of processes here now, we are going to go through the first process, which is at constant volume. So if you see through the vertical part now, volume is constant. When it is truly horizontal, like we have it now from 2 to 3, pressure is constant. So now we are in process 1 to 2 where volume is constant. So we'll take that process first. All right, so we have our solution for process 1 to 2. This is the process. Now, what's the condition for this? Constant volume. Are you there? Constant volume. This is what we have. Now, under constant volume, let's list out the given parameters over there. Work done, W from 1 to 2, which we can call W1 as the case may be, is equal to 0.0. You can put it kilojoule. Why? This is because at constant volume, work done is equal to 0. Don't forget this. When volume is constant, work done is equal to 0. Now, in this process, we were told that an amount of heat was supplied, so we call it heat supplied to the system between process 1 to 2. And that heat was given as 85 kilojoule, right? This is what we're given. And then the internal energy, change in internal energy, which is delta. This is unknown. So the first thing we want to find in this process now is to first of all obtain the change in internal energy. But let me quickly give us again another thing that was given here, as we can see. Now we're given the internal energy at point 1, internal energy at point 1, right? Internal energy at process point 1, right? Point 1. This internal energy U1 was given as 100 kilojoule. As I hope you can see it here. That's the initial. So the initial value of internal energy is given as this. We are now asked to find the one at 2 and then the one at 3. Okay, so all we just need to do now is to recall the first law of thermodynamics. Are you there? First, the first law of thermodynamics equation. And that equation states that, just recall that Q minus W is equal to change in internal energy. But don't forget that change in internal energy is always equal to U2 minus U1. Are you there? This is what we have. So now let's leave this guy here, somewhere here, so we can use it later. Now as we move down, to suit this equation to this particular process, we can say this is Q1 to 2 minus W1 to 2 is equal to change in internal energy. Now, to obtain change in internal energy here, this is Q1 to 2 minus W1 to 2. And then what is Q1? As you can see here, Q1 here is 85. Are you there? Q1 to 2 is 85. While work done is 0. So we just have 85 minus 0. And then we have this ax, 85 kilojoule. So remember, from the previous problem we solved before this particular one, the last question we solved before this particular one, in this same video, you find out that when we're asked to calculate for heat, when we already knew the value for the internal energy, we find out that at the end that the internal energy was the same as the heat transferred. Why? Because work done is equal to 0. So understand that at constant volume, heat transfer is always equal to internal energy because work done is equal to 0. So when you remove 0 from heat, whatever you have remains as your internal energy. I hope this is clear. It finished like this. Now the next thing we're gonna find here now, since we know U1 and we are asked to find U2, we can just come here now and say recall. I can say, okay, to find U2, recall that U2 minus U1 is equal to change in U. And then we already know that U2 is what we are looking for, so this becomes change in U plus U1. Are you there? It's as simple as this. Now remember that change in U is what we just obtained just now, which is change in internal energy. And then U1 is given as 100. So all we just need to do now to find the internal energy at point 2 is to what? Add these two values together, 85 plus the value of U1 is 100. And by the time we add this together, this will give us 185 kilojoule. So this is the internal energy at point 2. So we have been able to find internal energy at point 2 now, given the one at point 1. So we are left with internal energy at point 3. I hope you are following me up. All right, so having done this now, the next thing we want to do is to quickly dive into the second process. Now, I said the system rejects this of heat at a constant pressure. That process where we have constant pressure is process 2 to 3. This is when pressure is constant. So we'll now take process 2 to 3. I hope you are here, please. Process 2 to 3. And what's the condition for this process? At constant pressure. Now, under this process, we are also given that work done from process 2 to 3 was given as 20 kilojoule. As you read through now, if you check the question, we are given, now the system rejects this heat, and then at constant this and this of work was done on it. Work done on it, not by it. That means because this work is done on the system, we are going to take this 20 as negative 20. Remember, whenever work is done on the system, the work done is negative. Only work done by the system is positive. I hope this is clear. So we'll take this guy as negative. Then now, heat under this process. Heat. Now, if you check now, the heat on this process is heat rejected. So let me add this now, heat rejected, which is Q1 to 2. And this would have given us minus 90 kilojoule. Please let me take you up so that you see this for yourself. Now look at the question very clear. Now the system rejects 90 kilojoule of heat. So anytime heat is rejected, you take it as negative. I hope you have been able to get the condition to which I'm applying this negative sign, right? Okay. So again, we need to find the internal energy between this process. Remember, if I come up with a sketch here like we have, as you can see on the screen now, this is 0.3, and then this is this is 0.2, all right? And then the flow is like this. So it means that the change in internal energy here will be equal to U3 minus U2. I hope you can see it. This is what we are going to have, because 3.3 is the final, 0.2 is the starting point, just as you can see now, process 2 to 3. So this is how we are going to get this. So first thing we need to find here now is the internal energy, which is change in internal energy at this particular point. Are you with me? All right. Change in internal energy is equal to unknown. So we just need to remember again the equation of first law of thermodynamics, which says that Q minus work done is equal to change in internal energy. And as you can see now, we have already defined the change in internal energy for this particular process, as you can see here, right? And then all I just need to do now is to make change in internal energy the subject of formula, and then let's make this equation look like this process. So this is automatically 2 to 3 minus W 2 to 3. And now all the work done is given, and then the heat is given. So automatically this is minus 90 minus 20. And then by the time we clear off the bracket, we have minus 90 plus 20. Then the answer here becomes minus 70 kilojoule. So this is the change in internal energy between process 2 and process 3. But between this, for this internal energy or change in internal energy, we won't be able to find U3 using this model I just put here under this line, as you can see, right? Because we're asked to find the internal energy at every point. So just say recall again that change in internal energy for this particular process will now be U3 minus U2, because U2 is the starting point, as you can see here, process 2 to 3. Now all we just need to do now is to make U3 the subject of formula, and if we do this, we have change this guy is equal to change in internal energy plus U2. And then what is our change in internal energy here? That's just 70 we obtained. And then for U2, we calculated this earlier to be 185, as you can see here, right? So we come down here and then put in the values. 185. By the time we sum up these two values together, automatically we'll have this as 115 kilojoule. So we have been able to obtain the all the internal energies, right? So as we can see now, the question requests that we find all the internal. So internal energy 1 was given as 100 kilojoule. Now internal energy 2, we just calculated this to be what? 185 kilojoule. Then internal energy 3, we just calculated this as 115 kilojoule. So we have gotten all the internal energies. But meanwhile, we have not actually finished this process. All right, we have not finished this process at all. Now the question, remember, we have not actually find work now, right? We have not actually find work because we are actually asked to find the adiabatic work. It is now from 3 to 1, that is adiabatic. It is neither at constant volume nor at constant pressure. You can see the line that is curved from 3 to 1, from 3 back to 1. So it shows that 3 is the starting point, while point 1 is the finishing point. Are we there? So if this is clear enough, all we just need to do now is to move over to this point and then begin to solve this. So for process 3 back to 1, as we have now, this process is what? Adiabatic process. So now for this adiabatic process, like we have, for any adiabatic process at all, heat is neither supplied nor rejected. So it shows that heat is equal to 0. Don't forget this, for any adiabatic process, no heat supply, no heat rejected, no heat is accepted. So it shows that heat here, which is Q from 3 to 1, is equal to 0. Understand this is a law that for any adiabatic process you are dealing with at all, there is no heat supplied, there is no heat rejected. I hope you understand this very, very clearly. Then we now have work done. Now the work done between this process, we call it 3 to 1, and then this is unknown. And then again, we now have our change in internal energy. So change in internal energy, let me just use the symbol ahead, and then this will now become U1 minus U3. You remember? Final, because in this case now, this is what we have. So it's now from 3 to 1. Can you see this diagram I just draw here, sketch? So this is how the flow is. That means change in internal energy from here becomes head minus tail. Can you see it? Head minus tail. That was how I arrived at this change in internal energy. So since we already know change in internal energy 1, and then we already know change in internal energy 3, all we just need to do in order to have this done is just to put in the values. For this guy, we're given 100. And then for this other guy, we just calculated that is 115. I hope you understand this. By the time we remove 115 from 100, this would have given us minus 15 kilojoule. So this is the internal energy. Again, all we just need to do in this process now is to recall the equation of the thermodynamic first law. Are you there? So the thermodynamics first law equation states that Q minus W would be equals to change in internal energy. So we can actually rearrange this to suit this particular question or this process. So we can have this as Q 3 to 1 minus W 3 to 1 is equal to change in internal energy on this process. Because we are looking for W, we can just make it the structure of formula 3 to 1, and then this gives us Q1 to Q3 to 1 minus change in internal energy. I hope you can see this. All we just need to do, guys, is to substitute in the values. So remember that heat is equal to 0, then minus change in internal energy as we just obtained is negative 15. You can see it here. We have change in internal energy for this process as negative 15. So we just come in here and put in minus 15. And then if we clear off this bracket, we have 0 plus 15. And then this would have given us 15 kilojoule. This is it. So this is the work done here. This is the work done. It's as simple as ABC. Simple as ABC. All we just need to do now to ensure that we summarize this problem is to say hence, comma, adiabatic work is 15 kilojoule. That's all. Then what about the internal energy? Although we did this before, but let's just do it now. Internal energies. Are we there? So these internal energies, we have U1 is equal to 100, which was actually given from the question. U2, we calculated this to be 185 kilojoule. Can I show you that? So look at where we calculated for that here. So you see it here. So we have 185. 185. So you see it here, 185. So that's U2. Then U3, we calculated that to be what? 115, just as you can see here. Okay. So we have U3 is equal to 115 kilojoule. So these are the 4 things that we are asked to actually calculate via this particular question. So as you can see, it's very, very simple. So simple. Only that you just need to understand some basic conditions, and once these conditions are understood, you already have an upper hand. So guys, thank you for watching this video. Please, if you are yet to subscribe to this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting content. So guys, we love you, we love you, we love you, we love you. Make sure you give us a thumbs up, make sure you share this video, and make sure you leave a comment at the comment section. Thank you for watching. I will see you in the next module, where we will continue solving other problems in engineering thermodynamics. You can kindly check the description below and see if you will find the link to the next video. We love you guys. Thank you for watching. See you guys in the very next class. Bye.